When you learn a topic, particularly in science context, you tend to learn it as a kind of isolated island as a topic. It's, a unit all unto itself. It has a beginning date, it has an end date, maybe there's a test in a lab in there, and then when the unit's over, the topic is over, and you don't see it again until the exam, or if you take another physics class like in college or something. And I think that's a shame because these topics are really more closely related than that. And I don't just mean because they're all science topics. I mean because if science is the study of the material world, and physics in particular is trying to study how the material world works, assuming that there's logical and mathematical rules and trying to discover what they are, then they should all be, related to each other. If it's all part of one interconnected whole, then what atoms do and what cells do, well, they should be related to each other. If everything is connected and interrelated as part of the whole system, then what gases do when they heat up and what electrons do when they absorb light, they should be connected somehow. And in fact, they are. And when you learn how they're connected, it has a way of enriching them both. It has a way of deepening your understanding of each of them because it builds the background that they fit in. Well, I've set something up here. This is my attempt at illustrating the first scientific model of the atom. We're beginning a unit on electricity, but I don't want to let it just be an island. I want to connect it to something else. When you're learning about atomic models, you're usually learning about, materials. Maybe it would be in the same section of a chemistry class where you're going to learn the periodic table of the elements or something. But the development of atomic theory was happening about at the same time that developments in electricity and magnetism were being done. So they were happening around the same time, often in the same place, sometimes by the same people. So let's take a look at electricity and magnetism, but from this point of view. This is how someone would have imagined atoms would look in the early 1800s. This model was proposed by John Dalton in 1803, and as the first scientific model of atoms, it described them very, very meagerly. It imagined them kind of like they are here, just as tiny, indivisible beads. I'm using plastic beads here, but say you've got two different substances, two different elements. The only difference between those two elements would be the mass of their atoms. All of the atoms of one element would be identical with each other. All of the atoms of the other element would be identical with each other. And the thing that distinguishes element 1 from element 2 is that the atoms of element 1 have a different mass than the atoms of element 2. They combine in whole number ratios to form different compounds. That was an insight from chemistry, which was another developing science at the time. They are indivisible, which actually is what gives it the name atom. It comes from a Greek word meaning indivisible. And by and large, that's the concept of atoms that worked for the 19th century. And then someone had the bright idea to hook up a glass tube full of a gas to a strong voltage source, and something like this happened. So what I did was I just picked up the surface that these were laying on and leaned it over. So a whole bunch of them rolled away, but some of them didn't move. So that's strange. Let me go back and get one of these that rolled away. So here, this one rolled away. This one stayed put. Let's see what the deal is with these two. So you might be able to see, you might not. I'll try and describe it to you. This is round. It rolls easily. This one, almost like a diamond, has cut faces. This one really doesn't roll. These two are different from each other in a way that is particularly meaningful to picking up this surface and making it uneven. So if I zoom back out and lift it up again, yeah, this one resists motion in a way that this one doesn't. And that doesn't necessarily prove anything other than that these two are different. And I've discovered a way to show their difference because they respond to something in two unique ways.